Okay, next exercise. Exercise 8.3, sigma notation. Series are often written in sigma notation. The Greek letter sigma, which is this letter, you've seen that since year 8 or 9, is the equivalent of an English S. And here this sigma stands for the sum of a series. Just a few examples. Evaluate the sum of the series. So this means evaluate the sum of the series starting from k equals 2 up to k equals 5. And this is the general term of the series. So first term would be 2 cubed minus 1. So, therefore, this series from k equals 2 to 5 of k cubed minus 1 would be, starting with k2, we've got 2 cubed minus 1, plus, this is the sum of a series, remember, then we've got k, when k is 3, 3 cubed minus 1, plus when k is 4, 3 to the power of 4 minus 1, plus when k is sorry, I've done this wrong. 3 to the power of 3. Sorry, here we've got 4 to the power of 3. So 4 to the power of 3 minus 1. And when k is 5, we've got 5 to the power of 3 minus 1. And evaluating that, if we evaluate each of these, 2 cubed minus 1 is 7, 3 cubed minus 1 is 26, 4 cubed minus 1 is 63, and 5 cubed minus 1 is 124, and adding all those together, we get 120, okay? Next example, example 2. Second example, how many terms are there in this series? N squared plus 1, starting from n equals 3 to n equals 9. So you've got when n is 3, so it isn't actually 6 terms, because if you count, we've got when n is 3, n is 4, n is 5, n is 6, n is 7, n is 8, and n is 9. So this is 1, 2, 3, 4, 5, 6, 7. 7 terms. So therefore, it's 7 terms in that series. So therefore, to find the number of terms, you would do 9 minus 3 plus 1. See, if you just do 9 minus 3, it's just the difference between 9 and 3. But if you want to count both the 9 and the 3, you need to do 9 minus 3 plus 1, which is 7 terms. So please be careful with that. Often the series might have a lot more terms than 7. With this, I was able to say count those like that. N is 3, 4, 5, 6, 7, 8, 9. You can clearly see there's 7 terms. I mean, if I do another one, let's look at this one, our previous example up here, from k is 2 to 5. Well, we've got when k is 2, 3, 4, and 5. So we've got 4 terms there of the series. We can see we had the 4 terms there. But if you do 5 minus 2, that's only 3. So therefore, if you just come back up here, so the number of terms will be 5 minus 2, but plus 1, which is 4 terms there. So we'll just come up with a little general formula for the number of terms. So for a series, little general sort of formula and reminder. So if you've got the series starting from n is q up to n is p of some function of n, the number of terms in that series will be p minus q plus 1. So don't forget to plus the 1. Okay, if you don't do that, then when you're doing some harder questions later and you need to know the number of terms in the series, you'll get it wrong. Okay, and last question here, to write 3 plus 6 plus 12 plus all the terms up to 3 times 2 to the n in sigma notation. Now, this last term is the nth term, 3 times 2 to the n. So basically, the nth term is 3 times 2 to the n. So we have to think what gives us to find where n starts from. Our first term in the series is 3. So for our first term, we've got 3. So 3 equals 3 times 2 to the n. Now, the only way that we're going to get work out what n is, 2 to the power of n is obviously 1. So dividing by 3, we get 3 divided by 3 is 1 equals 2 to the power of n. So this particular series starts with n is 0. Now, So to write this series in sigma notation, 3 plus 6 plus 12 plus all the way up to 3 times 2 to the n, we can't put n equals 0 up to n. So we're just going to choose another pronumeral like k or r. So we can say, well, this starts from our general term, we're going to call it 3 times 2 to the power of r, and it starts from when r is 0, so 3 times 2 to the power of 0 is 3, all the way up to substituting when r is n will give us 3 times 2 to the n. So don't put n equals 0 up to n equals n. You would use another pronumeral and change that general term of the pronumeral here to an r or a k or whatever you would like, okay? Look, I'm just going to do another 2 examples. Write this series here in sigma notation. Well, it looks like the first term in this series is 6, and the second term in this series is 12, and the third term is 18, etc. It looks like they're adding 6 onto each term in this series. So the second term would be 6 plus 6, and the third term would be whatever we've got here. It would be 6 plus another 6 times 2, for example. So actually, yeah, so the next one, I might actually start with a different, oh no, I'll keep it. So the third term will be 6 plus, we're adding 6 again twice, okay? And the last term, so we've got 6, then we've got 6 plus really one lot of 6. And this one is 6 plus 2 lots of 6. And the next term would be 6 plus 3 lots of 6. See, this 6 here is the first term, and this is going to lead us into our next exercise soon, okay? And so this 72, I'm going to call it my nth term, but I'm just going to put the 72. So this 72 must be 6 plus 6 lots of n. We're not sure what that n is, okay? So, subtracting 6, I've got 66 equals 6 lots of n, and so therefore n has to be 11. So here, for this term here, I've got n is 1, and down here, if this is what the general term is, so we're saying my general term, should put that in somewhere, the general term we think is 6 plus 6 times n. So the general term is that, there, and this particular general term would have n equaling 11. So therefore, writing this series in sigma notation, it's the sum of the series 6 plus 6 times n, or 6 plus 6n, starting with the term n equals 1 up to the term n is 11. So that's the answer. That's writing that series in sigma notation. So I could just put that is equal to 6 plus 12 plus 18 plus all the way up to 72. Okay? There, that from n is 1 up to 11 of 6 plus 6 to the n would be this term here. Okay? Just for one more example, example 5. Now, this particular example up here is an arithmetic series, and you'll discover what that is in the next exercise. And this particular term down here is what we call a geometrical series, or geometric series, and you'll discover what that is in a few more exercises, okay? Okay, and just for the last example in this exercise. Now, it looks like we're doing, I can rewrite this as 1 plus 1 over 3. So it looks like it's 1 plus 1 over 3 plus 1 over 3 squared, because that's 1 over 9, plus this must be 1 over 3 to the power of n. Now, this would be 1 over 3 to the power of 1. This must be 1 over 3 to the power of 0, because how else do we get 1? So we're looking, because we want to write the series in sigma notation, each term in the series must follow a particular formula. Okay, so this is the tricky bit here. So therefore the first term, or we can say, well, our first term is, how are we going to get 1? If I wasn't sure what to write here, how am I going to make this 1 be in the form of 1 over 3 to the n? If we put 1 equals 1 over 3 to the power of n and try and solve, we get 3 to the power of n is 1, so therefore n is 0, which is what we did there. Then we can look at this last term here, that 1 over 59049 equals 1 over 3 to the power of n, because the numerators are equal, the denominators therefore are, so 3 to the power of n is 59049. You could either take logs of both sides here, or you could guess. We'll take logs of both sides, so ln 3 to the power of n equals ln 59049. So n ln 3 equals ln 59049. Therefore, n equals ln 59049 over ln 3. And if we work that out, we get n is 10, okay? And so therefore, this series can be written as, we're starting from n is 0 up to n is 10 of the general term is 1 over 3 to the power of n, and that is equal to 1 plus a third plus 1/9 plus 1 over 59049. So writing that series in sigma notation. Now, I know that in my first video I said to you, well, series must always start from where n was a positive term. But for example here, this still is the first term of the series, but it just happens to have the value of n is 0. This is still the second term of the series, okay? That's why what we mean by for positive integers, that's the first term, that's the second term, even though it does start with the value of n is 0. That n is 0 is still the first term of the series, okay?